Yes. So we had this. I want you to see this as a tool. Why this is an important tool for us? Because when you look at the sine x over x, if you want to go to the quotient rule and so on, this is 0 over 0. And this, the squeeze theorem takes care of that indeterminate form. This gives you a strong tool in similar situations. For example, if I have limit of sine 3x over x as x approaches to 0. What about then? Okay. Now, for me, these are, or this is the mathematical fact I can refer to, and I want to turn anything similar to that to one of those facts and use the fact and resolve it. Well, the way I want to look at this is that, okay, sine of 3x, if it is 3x down there, then I'm in good shape because I'm close to this. To be able to say that is similar to that, I will multiply the denominator by 3. I have to also multiply the numerator by 3, yes? But the constant multiple rule or law says that I can put that 3 out. Yes, constant multiple. Now, I am close by because this is box. The only thing is this x. To be able to say that my setup is correct, I will do change of variable. I'll set 3x as u. So in other words, I have sine of u over u limit 3 out there. But on the other hand, I know that when x goes to 0, 3x also goes to 0. Yes? Or in other words, u also goes to 0. So I turned that other limit to, again, sine box over box going to 0. And we know that that limit is equal to 1. And 3 times 1 is what we were looking for. Another one, let me write another one and give you some time to think a little bit about it. And how about limit of x squared over sine x over sine of 5x as x approaches to 0? How about limit of sine 5x over sine of 7x? The fact we know here is this. I want you to work with these functions and turn them into 1 or 2 limits like that and use the fact to evaluate it. You will be given 90 seconds. I'm not expecting you to go all the way through. What I want you to work on, you're working alone or with your friend to figure out what is the starting point, meaning that how you can change or play with these functions and change them in 1 or 2 limits of this form so that I can use use that fact. Go ahead, 90 seconds. You're talking to a friend or you're working on something, writing something. I don't want to see anyone sitting there and looking at me. 30 seconds left.
You don't know?
Okay. Maybe I can hear one or two ideas that you want to share. How did you start this one? Did anyone start it? Did we have any answer, like final answer for this? Yeah? Okay, let's then go slowly. That's a good sign for me. How about we do this? We take one of these x's with this one, and the other one with this 5x. Yeah? Almost there. The only thing is that this is the other way around. X sine x. Well, if this is 1, the other one would be also 1, but I can show you how. This I can write it as sine x over x. Yeah? And this other one, okay, I bring 5x down, but then see that this is x, 5x, down there is x. I want to turn that one to 5x, but I divided the denominator by 5, so I have to multiply the numerator by, sorry, the denominator by 5 as well. And x goes to 0 in both cases. Well, this guy, applying quotient law, this is 1 over 1. This guy here, now I can see that I can turn it, 5x is u, x goes to 0, so u goes to 0. Sine u over u goes to 0. However, there is this 1 over 5 also multiplied to the whole thing. Okay. And that is, again, 1 times 1 times 1 over 5, which is once I get to this, then that's the fact. That's the reference point for me. That's the theorem for me. How about this one? Did anyone have any progress in solving that? Yeah. Pardon, what? 5 over 7. Can you tell us at least the first step? How did you start that? Aren't we missing? Well, we are missing 5x here, and we are missing 7x there in the denominator. But forget the 7 and 5. The key point is x, because the coefficients, I can fix it by doing that, yes? So we divided the numerator and the denominator by x, and we are getting closer to this idea. Okay, not very close, because this is 5x, this is x, so I have to multiply that by 5, and multiply the whole thing by 5. This is 7, this is 7. You do the substitution. 7x is equal to u, so we have sine of u over u. 5x equal to v. That's, so just one step here, I will write like that, and then this will be 5, 1, 7, 1. That's what you have. Any questions, any comments for me? Nice, yes? Once you have, please keep in mind, proof of this, which uses Squeeze theorem, but it goes a little bit nicely, not very complicated, but nicely involved. You really don't need to know it. What I am asking you here to do is to use this fact to evaluate the other ones. That's not very complicated. You're just trying to generate the pattern. Let me write the last one here, and then we start working limit of sine of x minus 2 over x squared plus x minus 6. X goes to 2. Go ahead. I'll give you another 1 minute. Again, the goal is not you solve all the way. The main idea is that to start it and try to identify the key point to turn that or part of that into this limit. 1 minute starts now. Don't sit there looking at the screen or paper. Do something. Talk to a friend if you don't know how to start it. 30 seconds left. Ten more seconds. Okay. Does anyone want to share their starting point? Yes, please. Factor denominator to x minus 2, x plus. Okay, let me factor this c. Sine. Where does that come from? Isn't this like that? Yeah? Yeah? Why did you start factoring it?
X minus 2 correlates with the x minus 2.
So you look at it as we did before. 0 over 0, you try to get rid of the vanishing factor. Vanishing factor is x minus 2. So I can try to do this thing. But I'm not done, because canceling here in the numerator, I have sine of something. I cannot cancel with x minus 2. What I do then is, well, I think it is now clear based on I take this with that, and then the rest. The rest doesn't matter actually what is the rest, because that part, you can just apply the quotient law there, yes? Here, as x goes to 2, 1 over x plus 3 is? 1 over x plus 3 as x goes to 2 is? 1 over 5. So this part is the quotient law, and it's straightforward. The part that is not very obvious is this. But you already have the nice factors there. Basically, this time, what you need to do is set u to be x minus 2. And see that when x goes to 0, x minus 2, or u will go to 0. Oh, sorry. When x goes to 2, that's what I have, then u goes to 0. So we turned this limit to sine of box over box as box goes to 0. And the other part is 1 over 5. So we don't need to be worried about the rest of that. And sine u over u as u goes to 0 is? 1. So then we get 1 times 1 over 5, which is 1 over 5. Any questions, any comments? Why is this limit, other than, okay, yeah, it is giving us, in some ways, it's giving us a calculational tool. But why on earth someone should think of this limit to start with? Well, you all know the answer. If only think of, I don't know, 100 years ago, you learned about the trig function. You learned about differentiation, 150 years ago maybe. And now someone is saying that, don't you say the derivative of x squared is 2x? Why don't you find derivative of sine x? Okay, I say, let me start from the derivative at 0. How about that? Let's see if I can do only 1 point and then. So in that case, I have limit, remember, this is f at x minus f at 0 over x minus 0 as x goes to 0. And then plug in this stuff there. Limit of f of x is sine x. What is sine of 0? Sine of 0 is 0, so I don't need to write it up there, over x. That is the limit. Sine x over x is basically the limit that defines derivative of the function sine x at 0. Or in other words, if someone is interested in finding the slope of tangent line of the function sine x at 0, you have to evaluate that. And that's why the work needed here is a necessary work. It's a little bit of good ideas there. It may look a bit complicated, but it's absolutely necessary for us to be able to do that, to be able to find the derivative of sine x. Well, this is a bit cheating. You gave us the derivative of sine function at 0 only. How about the other points? Well, let's do the other points. It's not going to be far from this point. What if I want to find derivative of sine at a general given point A? I will use the other definition here. A plus h minus sine of A over h as h goes to 0. I have to evaluate that limit there. Sine of A plus h. Can I do something with that? Sine of A plus h. Factor what? The h out. remember, addition formula for sine, cosine weren't easy formulas. Those need some work. But we can use it here because this is sine of A cosine of H plus sine of H cosine of A minus sine of A over H. That is the addition formula for function sine. And now I want to separate this into pieces. This piece here, I want to put them together, and the other piece together. So I will have two limits. Limit of sine H, this part, times cosine A over H. H goes to 0, plus limit of, here, sine A cosine H minus sine A. Factor out sine A, and you'll get sine A cosine of H minus 1 divided by H. H goes to 0. I don't need to draw that line all the way. I can write it like that. Sine H over H, as H goes to 0, this limit, remember, A is a constant, yes? Pi over 2, pi over 10, 2.5, whatever. It's a number, so cosine of that number is a number. So it will come out of the limit, and we will have just cosine of A. Sine H over H as H goes to 0 is 1. Okay. How about this part? Okay, I can take away the sine A. That's okay there. Now I have to evaluate this limit, cosine H minus 1 over H. Let's quickly do this one. I will be able to do it on this board. Limit of cosine H minus 1 over H as H goes to 0. So let's see how we can deal with this one. First thing to note there is that cosine H as H goes to 0 is cosine of H is 1. It's cosine 0. Cosine 0 is 1. The numerator is 1 minus 1. The denominator is 0. So we are dealing with 0 over 0 case. Can I turn this in some ways to sine? Is there any way that, because that's the only limit we have trig functions in the numerator and then some x in the denominator. Yes, I'm trying to use the fact that we have. Is there any easy way to turn cosine H to sine H in that limit? Yes, please. Multiply and divide by?
The top and bottom by cosine H. To get like cosine squared.
If I multiply it by cosine H, I will get cosine squared minus cosine. But I'm going to do that cosine. You're very close, actually. You multiply the numerator and the denominator, not by cosine H. Remember the conjugate thing? The reason I'm doing this, when I multiply this to that, I will get cosine squared H minus 1 squared. And in the denominator, you will have H cosine H plus 1, yes? Why does it make a change if I turn it to cosine squared minus 1?
Identity.
The identity, Pythagorean theorem basically, yes? That guy is, this guy is nothing but negative sine squared. The other part, I can separate it and write it as cosine h plus 1 as h goes to 0. Yeah? Everything is nice there. The only point here is that now instead of sine h over h, we have sine squared over h. Yes, please. This is h. Sorry, yes, it should be h. That's a typo. Thank you. The only thing is that there is 2 signs multiplied up there rather than 1 sign. Well, how about I take that 1 sign out and just write it here. So negative sine squared, I wrote it as product of sine and negative sine h. Yeah, it's a bit of long work, but remember this. This trick is going to help you because this will get you closer to that trig identity or the Pythagorean theorem, and you can turn sine to cosine. Here, the first limit, what is the value of first limit? 1. What is the value of the second limit? 1 over 2, that's just quotient law. Cosine of 0 is 1, 1 over 2. What is the limit of the last one? Sine h, as h goes to 0 is 0. That's sine of 0, 0. This part is 0. So then we got cosine a. Weren't we interested on that? Derivative of sine functions at point A is cosine A. Is it really different story when we try to do cosine derivatives? Not really. Everything is going to be along the same lines. Actually, you can turn cosine to sine by the symmetries, yes? And then use the facts about it. This is the only limit you need to know to be able to find the derivative of sine function. Cosine, once you know sine, you know cosine, you know tan, derivative of tan, you know derivative of cosine, cotan, derivative of secant, cos, everything else comes from that. That's why sine x over x is playing very important role. And I want to now write down the derivatives of trig functions so that you can work with them as we go from this point on. Derivative of sine x, we just learned this, cosine x. Derivative of cosine x with a similar work can be shown is negative sine x. Derivative of tan x is secant squared, or equivalently, you can write as 1 plus tan squared x. Derivative of secant x, you know, once you know sine and cosine, these are all just quotient rule. Quotient rule you apply, you get all these ones. Derivative of secant is secant x times tan x. Derivative of cotan x is minus cosecant squared x, or negative 1 plus cotan squared x. One last one. I'm sorry, I'm trying to fit this one in so that I don't use the other boards for this one. Derivative of cosecant x is minus cosecant x cotan x. If I apply chain rule to this, I can get a bit more general versions of this. What does chain rule mean? It means that you not only can find derivative of sine x, but also derivative of sine of a function, sine u. And remember, the chain rule said that derivative of inner one times the derivative of outer one. In other words, if you see a different function there, this will still apply, cosine of u, but you have to multiply it by the derivative of inner one. F prime times, sorry, g prime times f prime of gx. And then derivative of cosine u is minus u prime sine u. Derivative of tan u is, I will just write this one, u prime secant squared u. Derivative of secant u is u prime secant u tan u. You know how to write these other two. I won't bother writing them down, but you already know the rules. What should I do with those ones? First, you have to know it by heart. This is now new items in your differentiation table. Remember, our goal is to turn you guys, chapter 3 means turn these students to differentiation machines. So you have to have tons of tools. Whenever I give you a function, actually, you know what? At some point, you will notice whatever I give you, you differentiate without looking at the question. And this will be something in the final exam, midterm as well. You guys are going to be always differentiating. That's good. Any questions, any comments? Yes, please. Aha. For inverse, I need to work a little bit on the inverse in general. That's what we will do on Wednesday. Yes. So finding derivative of sine inverse, cosine inverse, log function, all those ones we will do on Wednesday. Yes, please.
Memorize this, we don't have to like use.
What part of that was difficult? No, we won't ask you to show that proof, but I may ask you to do this one. This is not very complicated. Yes, you turn this one down there. Or I may ask you to, where was that? I may ask you to do this, for example, for finding derivative of cosine x. By the way, look at this thing that we calculated. This is derivative of cosine x at 0. We already did that. Yeah? I don't see this as something that I will ask you again, but pieces in this are basically the assignments. They're not very complicated. Maybe putting all together and seeing the big picture could be a problem. But looking at these each step, we are doing very simple calculations. Okay? I think if I can convince you that Math is always small, simple steps. I will go and sleep happily at night. Yeah? No, you don't. Okay, I want to sleep happily at night. That's I take my lesson there. Okay. Let's do some differentiation. Find the derivatives of the given functions. These are examples. You should know the rules by heart, and you have to be able to differentiate when. Oh, by the way, derivative of e to the power t, maybe I didn't, I'm not sure if I did put it in my handout or not, but let me write this one also here so that derivative of e to the power x is e to the power x. So that's one function. The other function is you only need to apply the rules. Go ahead, please. I'll give you 2 minutes. Go step by step. Chain rule, product rule, quotient rule, and do differentiate those ones. Go ahead. I'll give you 2 minutes. At least work. You have to be able to work on 2 to 3 of these ones before I write them down. Thirty seconds left. You don't need to simplify, by the way. You just try to apply the rules, get all the pieces of the rules differentiated, and then leave it as is. F prime at t. There are 2 functions, so I differentiate the first one plus differentiate the second one. So I'll write it in 2 pieces. This one is product of 2 functions. Derivative of first one, 1, times second one, plus the first one times derivative of the second one, cosine t. That is only this part here. Plus derivative of first one, derivative of e to the power t is e to the power t times the second one plus the first one itself, derivative of cosine t is negative sine t. So I'll take this one negative sine t. G prime x, quotient rule here, derivative of numerator secant squared x times this minus derivative of numerator times denominator minus numerator itself times the derivative of the denominator, 2x plus 2, then x squared plus 2x squared. Should I simplify? Don't simplify. Actually, in some questions, we will clearly tell you that do not simplify when it comes to differentiation. We want to see what you have done there. I will leave this one to you guys. This one, f prime of t is cosine of something, so the derivative would be the derivative of that something, u prime, times derivative of cosine is negative sine. Now you have to plug in u into that. Okay? That's just chain rule. Chain rule applied to the cosine. Now the derivative of the numerator. Derivative of e to the power t is e to the power t sine t minus derivative of the denominator cosine t times the numerator over sine squared t times sine of et minus 2 over sine of t. Well, if I write down hundreds of examples, at the end it comes back to you to make sure that practice, remember the differentiation rules, and remember the derivative of trig functions. Any questions? Yes, please. Yes, you're right. Sorry, I did put it here, but when I was transferring down, you're right. Thank you. Yes. Yeah. Thank you very much. Let's do one more. Find the tangent and equation. Find an equation for the tangent line. Tangent line of what? Tangent line to the curve given by y equal to e to the power x secant x at what point? At 0, 1. Find an equation for the tangent line. You need to know two things, yes, whenever you're trying to write an equation for a line. First of all, a point. Here's the point. But when we are talking about tangent lines, the first thing to check is that point a point on the curve or not? So note that if x is equal to 0, then y is going to be e to the power 0 secant 0. E to the power 0 is 1. What is secant of 0?
1.
1 over cosine 0. Remember this. So e to the power 0 over cosine 0. And cosine 0 is 1. So the first thing to check, this is important, because if that point is not a point on the curve, we are in trouble. So 1, 0, 1 is on the curve. The second thing is the slope of the tangent line. We know that the slope of tangent line is the derivative, that's another way of writing derivative, dx dy, when x is equal to 0. Okay? So here, the derivative of this guy is the first derivative, derivative of e to the power x is e to the power x, times the second one, plus the first one, derivative of secant is secant x tan x. Then after you differentiate, set x equal to 0. And this gives me e to the 0 secant 0 plus e to the 0 secant 0 tan 0. This is 1, this is 1, 1, 1, 0. So this whole thing will be 0, and that will be 1. You have a slope, you have a point, you can write the equation or an equation for the tangent line. I will leave it here, or let me complete that. That's what you need to know. Have a great day. See you all on Wednesday. Thank you very much.